So with an inductor, the inductor is trying to keep the current the same in the circuit. It doesn't allow all of the current to flow immediately when we close the switch and apply a source voltage. However, once that current does get established, the inductor wants to keep that current going. Okay, so notice when I close the switch, what we'll see is there'll be current coming from the source, and then some of that current will go through R2 and some through R1. Now, the current through the inductor, like I said, is going to be slow to get going, but eventually that inductor is going to look like a short circuit. So we say that in steady state, our inductor looks like a short circuit. So if you want to know what the current through the inductor is going to be at steady state, you need to redraw the circuit and envision that as its steady state equivalent. Okay, so redraw at steady state. Okay, so I'm going to draw the same circuit, and this time I'm going to actually show the inductor right here as a short circuit, and that's where my current would be if I were measuring that in steady state. The resistors are the same here, and 10 volts. All right, so in steady state, I would do this analysis where we would say the inductor looks like a short circuit. Okay, so at steady state, what is going on in my circuit? Well, this 10 volts is in parallel with R2. So I've got 10 volts there. The 10 volts is also in parallel with R1. So I've got 10 volts there as well. The inductor looks like a short circuit, so that's really just connecting that resistor R1 to ground. Okay. Whoops. Put that back. All right. So in steady state, we see that VR2 is 10 volts and VR1 is 10 volts. So that tells us that our current through R1 would be 10 volts divided by 2K, or 5 milliamps. Our current through R2 is also 10 volts and also 2K, so that's another 5 milliamps. Now, how would we find our current coming from the source? Right here. If we found our total resistance, which again is our 2K ohm resistor in parallel with our 2K. So we've got 1 kilo ohm total, and then our I sub S would be the total voltage divided by that total resistance, which we have 10 volts divided by 1K, which is 10 milliamps. And that makes sense because we've got 10 milliamps coming into a current divider, 5 milliamps this way, and 5 this way. So these are my steady state conditions. Okay. Now, that doesn't happen instantaneously. It takes some time for this to happen, just as we learned for the capacitor. And what happens between this state 1 and this state 2 is what we call the storage phase. Okay, and it takes some time for this to happen. So we're going to need to figure out how long it takes to happen. All right, so we need to find the time constant for our resistive and inductive circuit here. Now to find the time constant for an inductor, you're going to divide the inductor value by the resistor. That is different from what you learned for the capacitor. It's L over R. Okay, so we've got our 10 millihenries. And the R we're going to use this time is just R1. Now, if you had learned about Thevenin and a theorem that we call Thevenin's equivalent circuit theorem, you would know which resistor to use. Since we have not done that, and we won't get to that in this class, I will actually give you the fact that I want you to use R1 there. So if you need to know, I will tell you that. So what we find is that the time constant for the circuit is 5 microseconds. Now, is that the total time it takes to get from here to here? Not quite, okay? Remember, that's going to take 5 time constants. Total time to steady state is 5 times tau, where tau is 5 microseconds. So that tells us it's going to take 25 microseconds to get from circuit 1 to circuit 2. It's still very fast, but it's going to take that kind of time. All right, so initially, going back to circuit 1, initially, right when we close the switch, so I'm going to say at t equals 0 seconds, we just closed the switch. Something kind of interesting is going on. First of all, the current is trying to go through that inductor, but originally the inductor is going to push back and try not to let that current change. So right at t equals 0 seconds, the current through the inductor is actually going to be 0, just for that split second. And then over time, it's going to grow to the, oh, I'm sorry, not the I sub s. It's going to grow to be the 5 milliamps that we have here. Okay, but that's going to take some time. So let's kind of map out what's going on with our I sub L. And these are called the storage equations. So if we want to figure out what happens between here and here, that would be your storage equations. Okay, so the current through the inductor is going to start at 0 and go to a maximum value. So that equation is 1 minus e to the minus t over tau, and tau, remember, is 5 microseconds. Now, what is that maximum value we're going to? That's right here. That's the 5 milliamps. So I'm just going to put that right there. The voltage drop across the inductor, well, let's think about this. Okay, let's think about this. If the inductor is not allowing any current to flow through it at the very onset, that means this is like an open circuit at first. And what would we expect to measure if that were an open circuit? Well, that would be 10 volts, because there'd be no current, no voltage drop across R1 because there's no current there. And we would simply be measuring in parallel with the source. So we would be starting at 10 volts and then going to 0. So that's this equation right here, e to the minus t over tau. And then the voltage drop across R1. We're starting at 0 current through R1, so that would mean we're starting at 0 volts. And then we're gradually going to get to the point where we've got 5 milliamps of current through R1. So eventually, at steady state, we'll see that we have 10 volts across R1, but it's going to start at 0 and go to a maximum value, which is 1 minus e to the minus t over tau. And then VR2, I'm going to leave the source current out for just a moment, but what's going on with VR2? Well, we know that in steady state VR2 is going to be 10 volts. We know that. However, what's going on at t equals 0 is that once we close that switch, R2 is now in parallel with the source. So we're going to see 10 volts there, not only at t equals 0, but also at steady state, and it's not going to change between the t equals 0 and the 25 microseconds it takes to get to steady state. So that's just going to be 10, and it's not going to change. It is not time dependent. Okay. So that's the steady state. So whenever you want to know about what's going on in the steady state, you would need to redraw your circuit with your inductors, if there's more than one, looking like a short circuit. The storage equations describe what's happening after you close the switch up to the point where you reach steady state. And that's where you have your current starting at 0 and going to a maximum. And same thing for the voltage across the resistor that's in series with that inductor. Your voltage across the inductor is doing the opposite. It's going to start at a maximum and go down as it becomes a short circuit. Okay, so let's talk about the release phase. And I'm going to take a minute to redraw my circuit here. And we'll talk about the release phase. And our 10 millihenries. All right, so in order to analyze the release phase, the most important thing to know is what is IL at the time we open the switch. Okay, so let's head back up for just a minute here. So if we got all the way to steady state here, then we know that the current through the inductor is 5 milliamps. If we opened the switch before we got to the 5 milliamps, we would start from there. Say we only got up to 3 milliamps, we would start from 3 milliamps and go back down. But for a maximum of 5. So let's say we allowed our our circuit to reach steady state. So we're going to say that IL is the 5 milliamps. Now this is the key to understanding what happens in the release phase. Okay, so keep in mind this is what's been going on in the circuit. I've allowed enough time to have 5 milliamps here. What else is happening? I've got 5 milliamps here, and I have the 10 milliamps here. All right, so when I open this switch, let's say I'm going to open up that switch. I want to keep my 10 right here. Now, I don't have 10 milliamps there anymore, right? Because I opened the switch. There's nowhere for that current to go. So I'm taking that away. All right. Now, here is the key that I told you about. Whoops. Here is the key. IL is 5 milliamps. The key is that this 5 milliamps right here That is what the inductor is trying to keep moving through my circuit. So this 5 milliamps doesn't matter at all. Okay, that's old. That's history. That's what was going on. It is not anymore because our inductor has now taken over, and it is supplying current to our circuit. So the only thing that matters anymore is the 15 milliamps here. Okay. I'm sorry, 5 milliamps. Okay, bear with me here. I still wrote the 15, didn't I? 5 milliamps. Okay. And that's all that matters, is the 5 milliamps. Okay, so what we're going to do is our circuit analysis based on the 5 milliamps. So that 5 milliamps, the inductor is going to continue to send that 5 milliamps through my circuit, which does not include the source anymore. So that 5 milliamps is going to go this way and then this way, and then back to the inductor. And then everything, as the energy is released back through the circuit, we're going to see everything go to 0. So IL, VL, VR1, VR2, all go to 0. So that would be e to the minus t over tau. Now we do need to find tau again, and in this case, again, it's L over R. In this case, we are actually going to use both of our resistors because they're in series. And again, I will let you know if I think it might be a little bit hard to figure out what resistance to use. I will tell you. Okay, so tau is 2.5 microseconds. So the release phase takes how long? It takes 5 times that. About 12.5 microseconds. So still very fast. Okay, so I can now put my time constant into my equation. And that's going to be the equation for everything. So everything's going to start at a maximum and go to 0. It's just a matter of finding what that time constant is and finding what that maximum value is. Okay, so some of this is pretty simple. So again, it all starts with the 5 milliamps that we have here. Now, if I have 5 milliamps through 2k ohms of resistance, that would mean that I would have 10 volts right there. Does everyone see that? VR2 is 5 milliamps times 2 kilo ohms, which would be 10 volts. I've got the same 5 milliamps through R1, and that's also a 2 kilo ohm resistor. So that's also going to be 10 volts. Now, I'm going to go ahead and fill these in. So I've got 5 milliamps through my inductor. And remember, this is the key to everything. So if I know this at every given time, I know the voltage drops as well. So VL, actually let's skip VL and come back to it. VR2 we said was 10 volts starting out and going to 0. VR1 is 10 volts starting out and then goes to 0. Now VL, let's talk about what's going on with VL. Remember, Kirchhoff's voltage law says if we sum the voltage rises minus the voltage drops around a closed loop, we get 0. So since my inductor here is acting like a voltage source, we're going to give it a polarity, call that V sub L, and then figure out our Kirchhoff's voltage law equation. So if I start here and I travel around my circuit, I have a voltage drop of 10. So I'm going to say minus 10 right here. And then I continue on to R1, I have another drop of 10, plus to minus 10. And as I continue traveling around the loop, I go from minus to plus, which is a increase of V sub L, and then back to where I started. So that has to equal 0. So what I find is that VL is equal to, if I move the 10s to the other side, I add those. So VL has to be 20 volts. So what I'm saying is VL is going to start at 20 volts and go to 0. Now that's very interesting when you see that we only started with 10 volts. And that's something very interesting about how the inductor works, and that is that you will see a voltage spike that's much larger than the voltage that it started with. Okay, so like I said, it's going to take us about 12.5 microseconds for our current to get back to 0. So what if we wanted to calculate each of these properties at 11 microseconds? That's just a little bit before we get to 0. So for I sub L, we're going to take that 11 microseconds and we're going to substitute it into our equation for T in each of these equations. Okay, so I sub L, 5 milliamps times e to the minus 11 over 2.5 means that we'd have about 0.06 milliamps. And VL, if we substitute 11 in this equation, 20 times e to the minus t over 2.5 microseconds, we should get down to about 0.24 volts. Very small at that point. We're almost at 0. And then VR1, if we substitute the 11 microseconds into this equation, we get 0.12 volts, and the same for VR2. Okay, so you should be able to calculate for every point in time, whether it's talking about the storage phase or the release phase for the inductor. And remember, at steady state, which is what we look at most with the inductor, we're seeing that the inductor would be a short circuit. So just replace that in your circuit